Hi, welcome back. We are going to pick up with chapter 4 here by working through the 5 steps of hypothesis testing, and we'll go through an example together. So just to remind ourselves about the logic of hypothesis testing, I'm going to give you another little example. Let's imagine that there is a real world and a matrix world, and you can never know for sure, for certain, which world you are in at any given time. So I just have to guess which world I'm in. I assume I'm in the real world. I assume I'm in the matrix world based on incoming information or my experience in the world. I do have some information that could help me out. I do know that blue jays are very rare in the matrix world. They're pretty common in the real world, but in the matrix world, maybe they couldn't get the CGI right or something, the likelihood of encountering a blue jay is actually less than 5% likely. It's pretty rare. It's not impossible, notice. I could absolutely see a blue jay in the matrix world. They do exist, but they're so unusual that there's less than a 5% chance that I would encounter a blue jay if I'm in the matrix world. So I'm going about my business, walking down the street, and I come across a blue jay. If this is you, what is your gut instinct telling you? I don't know about you, but if it's me and I see this blue jay, I think, I'm probably not in the matrix world. This to me seems like evidence, this rare piece of evidence, this thing that I encounter that's so unusual in the matrix world tells me I probably am not in the matrix world. I reject the notion that I am in the matrix world, and I have support for my hypothesis that I'm in the real world. So I'm gathering support for my hypothesis that I must be in the real world. I don't think I'm in the matrix world because I saw something so unlikely in the matrix world that I think I'm probably not in the matrix world. Okay, see how that works? This is equivalent to the logic of hypothesis testing. Right? If I witness an effect that's so rare in the null world, I reject the null and I have support for the research hypothesis. Okay, so how do we go about our hypothesis testing? We actually will use these 5 steps that are laid out in the textbook for you for every single hypothesis test that we learn about in this class, nearly, I think. So the first step of hypothesis testing is to restate your research question with a research hypothesis and then with the corresponding null hypothesis. The next step is to determine the characteristics of our comparison distribution to compare to my sample or to my individual of interest. So I want to set up my distribution so I can figure out, I can map on what I witness, my piece of evidence onto that distribution to determine how unlikely or likely it is. I'll determine what cutoff scores I should be using for my particular test. And remember, that's decided by the researcher. You can choose a significance level of 0.05 or 0.01 if you want to be more conservative. And the cutoffs will depend on whether you're using a one-tailed or two-tailed test. In step 4, I will calculate my sample's z-score or my individual's z-score. And then I'll put that z-score onto my comparison distribution, and that will help me decide whether I can reject or fail to reject my null hypothesis. So let's work through an example. I think examples are always really helpful. I want to test the effect of a new vitamin that I think will help infants walk faster, walk earlier in their lives. So I give this vitamin to a baby, and I want to see after 2 years, I observe them for 2 years, and I want to see if my participants who get the vitamin start walking earlier than the general population of babies. And I have to know something about the general population of babies. So here I know that population, notice we have population parameters mu and sigma here. Okay. Remember, that's a mean and the standard deviation for a population. I know that on average, babies walk at the age of 14 months. But there's a standard deviation there because we know that babies are all a little bit different. So the standard deviation of that distribution is 3 or 3 months. So in other words, babies typically start walking around 14 months, give or take 3 months. Okay. So let's see. We will work through this example using the 5 steps of hypothesis testing. In the first step of hypothesis testing, remember this is where we restate our research question as a research hypothesis and a null hypothesis about the populations. And this part is really important, about the populations. Who are the populations? Okay, so let's practice. The first population here is going to be the population corresponding to your experimental group. Okay, so in this case, if I think I'm going to give babies a new vitamin in my study to see if babies who get the vitamin walk sooner, right? Those babies in my study represent the population of babies who take this new vitamin. So we're always stating the populations in terms of the broader world, not about my study. Okay. So population 1 is babies in the world who get this new vitamin. And population 2 is babies in the world in general who don't take this new vitamin. The way that we write the research and null hypotheses now are going to depend on the way the research question was stated. So notice that our research question is specifically that we think that the vitamin is going to improve child development, right? So here I have underlined and bolded the word improve. That is directional language. I specifically think that babies who take the vitamin, population 1, will walk earlier or at a younger age than babies who don't take the vitamin, or population 2. So ask yourself if we should be doing a one-tailed directional test or a two-tailed non-directional test. Hopefully you said a one-tailed test, right? I'm looking specifically to see if child development has improved or if these babies will walk at a younger age, okay? So in other words, I'm going to look only in the lower tail because I want to know if population 1 has a lower mean than population 2. So note here that the research hypothesis will state that the mean age of walking, or the mean walking age, will be lower in population 1 than in population 2. And then notice that there's this little piece I tagged onto the end here. Mu with a subscript 1 is less than mu with a subscript 2. So mu sub 1 refers to the mean of population 1, and mu sub 2 refers to the mean of population 2 here. And then maybe you need to jog your memory about these symbols. But remember that this symbol here, the mouth of the alligator faces the larger number, right? So it eats the larger number. So here, if you see this symbol here, we read that as less than. So the mean of population 1 is less than the mean of population 2 is our research hypothesis. Okay. In the null hypothesis, remember we have to use the exact opposite language than the language we used in the research hypothesis. So the null hypothesis in this example is the mean age of walking, or the mean walking age in population 1 will be higher than or equal to the mean of population 2. Okay. And then we use this symbol here to say greater than or equal to. So mu sub 1 is greater than or equal to mu sub 2. Great, so those are our populations, and then we've restated the research and the null hypothesis. Let's move on to step 2 of hypothesis testing. In step 2, we determine the characteristics of our comparison distribution. Okay. You'll hear that term a lot, the comparison distribution for this test. Recall that for the general population, that's the population we want to compare our babies to, right? To babies in general. So the comparison distribution has a mean equal to 14 months and a standard deviation of 3 months. That's the comparison distribution, or population 2, the distribution corresponding to population 2. So the characteristics of this distribution are mu of 14 and sigma of 3. All right. In step 3, this is where we as the researchers determine the cutoff score or the critical value that I'll use for my test, because I'll actually be conducting the test in steps 4 and 5. Okay, so in this case, notice that we had a one-tailed test. We've already determined that. That's because I had a directional hypothesis. So I wanted to know if babies are walking sooner when they take the new vitamin. So that corresponds to a one-tailed directional test. I'm only looking in the lower tail. And then I want to conduct this test. I want to be pretty conservative. So I'm going to conduct this test at the P is less than 0.01 significance level. In other words, I will reject my null hypothesis if I witness a result in my study that is less than 1% likely to occur by chance. Okay. So in this case, why don't you take a look at this table and try to figure out which quadrant we should be working with. So we're using a significance level of 0.01, right? So that's this row. And I'm doing a one-tailed test, right? So that means that my cutoff scores here will be either negative 2.33 or positive 2.33. Remember that we are interested only in the lower tail because I want to look to see if my babies who take the vitamin or if babies who take the vitamin have a lower walking age, a younger walking age than babies in general who don't take the vitamin. So in that case, my cutoff score is going to be negative 2.33. And notice that that's labeled right here. So my cutoff score is negative 2.33 for this test. And I've shaded in the area under the curve for all the values that are more extreme than negative 2.33. Any value more extreme than negative 2.33 on this distribution is less than 1% likely to occur. Okay. That was by design, by the way I set this up. Okay. All right, now's the fun part. We get to actually do the test. In step 4, I determine my sample's score on the distribution. So for now, let's just say I tested this vitamin on one baby, right? Maybe financial limitations. And my baby began walking at 6 months old, as early as 6 months. Wow. So I'm going to calculate my z-score for my sample. Okay, so I'll use this familiar z-score formula. Okay. I'll calculate my baby's z-score. Excuse me. There we go. So 6 is x, the value of x, minus 14, that's the comparison distribution mean, over 3, the comparison distribution standard deviation. Okay, so I'm comparing my sample value to a distribution with a mean of 14 and a standard deviation of 3. Okay. If you do that calculation, you end up with a z-score of negative 2.67. So remember, this is our comparison distribution. The cutoff value is negative 2.33. My baby has a z-score of negative 2.67. So that's a little bit more extreme. Negative 2.67 is somewhere beyond my critical cutoff value, my critical value, or CV. Okay, So it is out in that tail beyond the cutoff value, or it's in the shaded region. Sometimes we call that shaded region the rejection region, which can help you determine what to do with that value. Okay, so now we want to determine if I reject my null hypothesis. This is step 5. For this step, I'm looking at 2 pieces of information: my critical value, or the critical score. So again, that was negative 2.33. And then my z-score that I calculated in step 4 is negative 2.67. Okay. So again, this is the same diagram that I had just drawn on the previous slide. My baby, my experimental sample baby, has a z-score that is more extreme than the critical cutoff value. Or in other words, has a score that falls in the shaded rejection region on my comparison distribution. So I conclude that, here we are, if the sample z-score is more extreme than the cutoff score, the null hypothesis can be rejected, and I have support for the research hypothesis. Okay? In this case, we've supported the hypothesis that the vitamin actually does improve development. Notice that we didn't prove that the vitamin works, right? But I do have support or evidence that the vitamin seems to be working, right? And that's because to see a baby walking at 6 months of age, just by chance, knowing the typical walking age for the population and the standard deviation of that population, 6 months of walking age is so rare, right, if the vitamin weren't doing something. So I think that the vitamin must be working here, or at least I have evidence, I'm gathering evidence that the vitamin is probably doing something to help my babies. Okay, so we could write up this research finding. We could write up this research finding and say that we think the vitamin might be working. Notice that I'm switching gears a little bit here. If we had asked a slightly different research question, if I had asked whether the vitamin changes child development, then I would be conducting a two-tailed test, right? And I could have conducted my experiment as a two-tailed test if I wanted to determine whether the vitamin changes development, right? If I wanted to know if it either helps or hinders development, then I could have conducted a two-tailed test. If I had made that decision as the researcher, it would change the way that I state my hypotheses, right? Specifically, I would say that the mean age of walking in population 1 will be different than or not equal to the mean age of walking in population 2. And then my corresponding null hypothesis would be that the mean age of walking for population 1 is the same as the walking age for population 2. Okay. Alrighty, that's the end of this slideshow, and let me know if you have any questions. Thanks.